So let's start with linear ODEs. That's going to be paragraph 2.2. And we'll start with a few definitions. So an ODE is linear if the unknown function and its derivative, if it's linear in the unknown functions and its derivative. So let me give you a few examples. Really easy to look at the examples. If you look at y primes equals 3y, that's a first order linear ODE. If you look at y prime equals 3y plus t squared, that's going to be a first order linear ODE as well. But if you look at y primes equal 3y squared plus t, it's the first order non-linear ODE because of the y squared. So in that variable, it's not going to be linear. Now, the ODEs we just gave, the four examples we gave with the pendulum, with Volterra, the economics, and the chemical equations are all non-linear, including the pendulum, because of the sine function. Right? So it's not linear. Now, it's not linear because of the sine function, but if instead of having the sine function, I just replace sine theta by theta, then it would become linear. But of course, I cannot replace sine theta by just saying, oh, you know, I mean, it would be so much better if it was linear, so let's just replace something non-linear by something linear. The reason why I could possibly do this is if theta is small, very small. Basically, you know the power series of sine, where sine theta is equal to theta plus minus theta cubed over 6, and all this, right? You know all this. So basically, you're saying sine theta is going to be theta plus something small. So if you are with a small theta, that's going to work out. Basically, in the video I showed, you can't do that. I mean, you know, the person was like, you know, holding the pendulum really high. That's not going to work out at all. I mean, so. But if you had a small variation, then you would have a linear ODE. It's called linearization. Okay, what I'm going to do is talk about dimension 1 and first order. So that's the first thing we're going to do. So dimension 1, d equals 1, first order. So that's simple. What I have is y prime, that's a proposition. So y primes equals a of t, y of t plus b of t. And I have an initial condition, so that's an initial value problem that has one solution that is given by this formula. It can be proven. I'm not going to do it here. So, you know, it's not very difficult to do. But what I would like to stress out is that you can always find the closed form provided you can find the antiderivatives. So in a sense, you know, finding the antiderivative is solving an ODE, right? So closed form antiderivatives kind of, you know, so I mean, whether you can find the closed form or not really depends on whether you have an antiderivative or not. So that's the first thing. If you have y primes equals a of t times y of t plus b of t. Of course, there is one very special case, which is when b of t is equal to 0 and a of t is a constant, say m. This is what we just discussed earlier, a very, very simple example of an ODE. You have y primes equal my, y of 0 equals y0, and then there's one solution, which is y0 exponential mt. Now, I just would like you to stop for a second and think about what happens for the various values of y0, right? There's obviously one value of y0 that is pretty special. That's when y0 equals 0. Because in this case, the solution is constant. It's constant equal to 0. So the solution is a constant function. This is called the stationary solution. Okay? In a sense, it's like an equilibrium, right? I mean, if you land there, then you're going to stay there. It's an equilibrium. Right? But you can ask another question then. It's like if instead of having y0 equals 0, I had y0 equals like something very, 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 very close to 0, like say 10 raised to power negative 1,000. We reach something really close. What would happen? It's a good question, isn't it? Well, you can say, well, maybe I will actually, I'm really close to 0, so maybe I will stick close to the solution, right? Would, you know, I mean, I'm not saying that's the case, but you know, that's, some people might think that. Well, it will depend on m. If m is negative, or if m is positive, we'll have different behaviors. To your left, you have what happens when m is negative. You start at 10 raised to power negative 4, which is here, right here. And then what you can see is you actually, as time goes, you actually get closer to the stationary solution. On the other hand, if you are on the right-hand side, when m is positive, you start really close to 10 raised to negative 4. Obviously, I mean, the scales are different here. This is like 10 to negative 4, and this is 10 raised to power 4. So you can see that, you know, in both cases, we start at the same point. But here, what happens is that very quickly, we just diverge. And of course, it doesn't take a rocket scientist, even though I hate this expression because rocket science is not more difficult than math. But I mean, it doesn't take a rocket scientist to figure out that, you know, it's m is positive, then exponential mt is just going to take over the y0. So what we have is a very different behavior if m is negative or if m is positive. If m is negative, what we have is something called astability. I start close to 0, close to the stationary solution, and then I will actually get closer to that stationary solution as time goes. If m is positive, well, then we don't have this astability. We have instability. It's exactly the other behavior. When we have a small disturbance of the initial condition, then we have a large variation of the solution. And that will be called on Wednesday instability. So, you know, when it comes to d equals 1 first order linear equation, there is not really much more to say. It's a very simple thing. Now, what I would like to do is to go to, I'm going to stay in dimension 1, but I'm going to do pth order. Second order, third order, 10th order. So again, dimension is 1, which means that I'm still dealing with functions from R to R. Right? D is the dimension of the space. But I will deal with equations such as this one. The sum from I equals 0 to p of ai yi, that's the derivative, the ith derivative, equals 0. So ai's are real numbers. And of course, the first one is not 0, otherwise it's not of order p. So we can just set ap equal 1, just divide everything by ap, and that's doesn't, you know, it's just easier this way. And the initial condition at this point is not given by simply y of 0, it's given by a bunch of y0, the derivative, and basically all the derivative that we need in order to have the initial condition and one solution only. So if we have p equals 3, then we will need y of 0, y prime of 0, and y second of 0 as an initial condition. That's an example of a linear third order dimension 1 ODE. So that's an example. What I will do here is to show you that this case can be replaced by the next case that will be first order dimension p. So we will not really deal with this case. What we will do is say this case is going to be dealt with. Oops, I'm sorry. This is not injective, is it? Okay. Much better this way. So this will be dealt with in 2.3.4. So how do I go from d equals 1 pth order to d equals p first order? It's actually pretty simple. If you look at the equation that you have here, which is y third plus a second, I mean a2 y second plus a plus a1 a prime, y prime plus a0 equals 0, then what you can do is say, I'm going to look at a vector u that will be given by y, the derivative of y, the second derivative of y. And what I will be able to do is to relate u prime and u. Then u prime is y prime, y second, y third. And what I'm saying is that that's going to be a matrix times y, y prime, y second. Right? For y prime, it's pretty easy. It's going to be 0 times y plus 1 times y prime plus 0. Y second is as easy. Now, the third line of the matrix is the one that will give me the, basically that will come from the equation. What I have is that y third is going to be equal to minus, basically y third is going to be equal to some, I missed a y here, I'm sorry. I was meant to say that's weird. So it's going to be minus a0 times y minus a1 minus a2. Right, so what I have really here is u primes equals this I'm going to call a, au. So instead of having a third order linear ODE with in R, I have a first order linear ODE in R3. And what I just did here, I can do it for any dimension exactly the same way. I just choose the u equals y to y derivative p minus 1. U prime is going to be this vector here, And then what I have is this matrix here that is basically the same as this one for dimension 3. Basically, it's called the transpose of the companion matrix for the ODE. And then what I have is just replaced the equation d equals 1 pth order by d equal p first order. Okay? So that's very simple. And here's another example. I don't know why I'm giving so many examples of this thing because it's pretty simple. But if you didn't get the first example, then you can go online on EduNow, look at the handouts, and that's there. Same idea. You have u primes equal au when you have u second minus 4y prime plus 3y equals 0. Then this is what you get. All right. So this is d equals 1 pth order. Let's go to let's go to 2.2.4, which is going to be d equals p and first order. So that's kind of silly to do d equals p. What I'm saying here is d is greater than 1. That's what I'm saying. Strictly greater than 1. So what we're going to do is first introduce the exponential of a matrix. So if we take a matrix, d times d, so I have d rows and d columns, then I can define the exponential of the matrix as what you would think you should define the exponential of the matrix. That's 1 over the factorial of k times a raised to power k, and you just sum them up. The first question, of course, is this is defined. I'm not going to get in. The answer is yes. You can prove it. And if you define the exponential of a matrix, then you can actually use theorem 2.2.8, Duomo theorem, which will state that if you have u prime equals a u of t, and u of 0 equals u0, then there is a solution, only one solution, which is going to be exponential TA times U0. So basically, in this case, you can just solve your ODE. I just spent like 5 minutes stressing out that you usually don't solve ODEs, and it's exactly what I'm doing now, but often you don't. In this particular case, you do, okay? So all you need to do is to compute the exponential of the matrix. Not very complicated. We'll get into that in a minute, but this is what we have. And you can even be a little bit more general in this by adding by adding a little bit to the AU of t and put B of t, and this is what you have. Then it complicates quite a lot the equation, but actually, you can just solve the problem. So if you have a if you have a first order ODE, which is linear in RD with d greater than 1, d equals 1 is obviously a trivial case here, then you can just solve this ODE pretty simply. Pretty simply, provided you can compute the exponential of the matrix. Now, to compute the exponential of the matrix, it's basically linear algebra, which I know all of you are very familiar with. Let me just go over this really quickly, just to recall you how you do it. So if you take this matrix A here, so you take A, what you have is what is called a Jordan matrix J. It's a triangular matrix, a little bit better than a triangular matrix because you can actually decide the blocks, and it's pretty nice. But in any case, what you have is that this J matrix is a diagonal matrix plus an N matrix, which is called nilpotent. And it means that when I raise this matrix to a certain power, then eventually that will become 0. Okay? So if you have this, and often the matrix, you have to go to the complex field to do this because otherwise it doesn't work all the time. But if you are in the complex field, you can guarantee the existence of J and of matrices P and inverse P that will actually do this. So what happens is that you have the A raised to power K, which will be A times A times A K times. You can just write this, the inverse of P, JP, the inverse of P, JP, all of this, all the way K times. And of course, what will happen is that this P and that P inverse will cancel out. And so will this one and this one. And eventually, I'm not very good in actually writing on the slide, so I'll just not do this again. So in any case, what you end up with is P inverse times your triangular matrix J raised to power K times P is equal to AK. So when you do the exponential, you just end up with this, and the exponential of Tj can be computed pretty easily. If it's a diagonal form, it's trivial. If it's a diagonal form, you just take the exponential of the diagonal elements. So it's very, very simple. If you're not familiar with this, then I suggest by Wednesday, a short video that was made at the MIT by Gilbert Strang, and the link is here, and I suggest you watch it if you're not familiar with the Jordan decomposition. If you are, don't waste your time watching something you already know. All right, now let me just go back to the example and see how it works. And the reason why I'm doing this example is also to show you something. I'm not going to spill the beans just for now. So just pay attention and you'll see why it's interesting. All right, so I go back to my equation y second minus 4y prime plus 3y equals 0 with y of 0 equals 2 and y prime of 0 equals 4. Now, this can be replaced by u primes equals au, as we said. Basically, what we have is u, which is, as expected, y prime. U of 0, which is the initial conditions. That's u of 0, u prime of 0, so that's 2, 4. And the matrix, which is 0, 1, negative 3, 4. Now, I compute the eigenvalues. For this, I compute the determinant of A minus lambda I. By the way, this is called a characteristic polynomial. And those of you who learn ODEs before doing linear algebra had something called characteristic polynomial, or second, whatnot. That's exactly the characteristic polynomial of that guy, right? So, the whole thing is, of course, makes sense. Then we have the eigenvectors that are 1, 1, and 1, 3. By the way, the spectrum of the matrix is the set of all eigenvalues. So here it's 1 and 3. It's denoted sigma. And so we have A equals P minus 1 JP, where J is this matrix here that is diagonal, actually. So I have a diagonal matrix here, and that's what we have. So now what I will do is I will compute the exponential of t times j. That's pretty easy to do. That's going to be exponential t, 0, 0, exponential 3t. Pretty simple. And I'm going to multiply this by the inverse of p to the left and p to the right. So this is what I get, 1/2 of 3 exponential t minus exponential 3t, and etc. By the way, if I had a discriminant that was negative, that means that I would have had complex conjugate roots, which means I would have exponential I something, and here sine and cosine would come into play. Now, what we have is that this happens to be exponential TA, but thanks to Duomo theorem, then I can just say that u of t is exponential TA times u of 0. Therefore, I just replace my, my little guy here, exponential TA, by the value I just found, times 2, 4. And, you know, that's u of t. So u of t, just remember that u of t is y of t, y prime of t. So I just happen to have y of t, right? I just make the computation to the right. So basically what I have is this, right? So now I make the computation to the right, and this is what I get. Y of t, y prime of t, and y of t is exponential t plus exponential 3t. And of course, y prime of t is the second component of the vector, which just happens to be the derivative of the first one, as you would expect. So what you can say is that y of t equals exponential t plus exponential 3t is the solution to this initial value problem, right? And if you have a doubt, in doubt, just verify, just take y, and just differentiate it twice, just verify the equation holds, and also check that y of 0 equals 2, and that y prime of 0 equals to 4. All right? Okay, so that's how to solve a first order linear ODE in dimension p. I just would like to show you something interesting. If instead of saying I really had the initial condition, just say I just had like y of 0 and y prime of 0. Forget about 2 and 4. Then what I would have had is y of t equals to this guy here times y of 0, and that guy here times y prime of 0. And that what you have is a set of solution that is a second two-dimensional linear space with y0 and y prime of 0. Okay? That's something I wanted to point out. Something else I would like to point out is what happens if I choose y of 0 and y prime of 0 equal to 0. Well, obviously, y of t is equal to 0 all the way, right? So we have a stationary solution. We have an equilibrium. We have a solution that is always equal to 0. Right? It's pretty obvious. But I have the same question as earlier. What happens if instead of having 0, 0, I'm close to 0, 0? Right? Earlier, if m was negative, then it would actually converge to 0, and if it was positive, it would go away. What happens in this case? Well, let's go back to the equation. The solution would not stay close to 0 because I have an exponential t and an exponential 3t. So that will just blow up. It will go all the way to plus infinity. So this is really these two coefficients here, the 1 here and the 3 here, that make it blow up. Can we trace this 1 and 3 back to where they came from? I mean, I'd like to just see where this 1 and this 3 is coming from. Because obviously, if you had negative 1 and negative 3, it would have been different ball of wax altogether, right? So where is this coming from? Well, it's coming from, remember we had this exponential 3t, and I mean TA that was 3 times exponential t minus exponential 3t. That's really coming from that Jordan matrix, that diagonal form with 1 and 3. But that really came from the spectrum of the matrix, from the eigenvalues. The eigenvalues were 1 and 3, so this is what we have. But if the eigenvalues had been something else, if, say, the eigenvalues had been negative, then, negative, or the complex part, the real part of the eigenvalue had been negative, then obviously what would have happened is convergence towards 0, right? So what it means is that a corollary to the Duomo theorem is this. If I have u prime equal AU with the notation we just introduced, then first of all, 0 is a stationary solution. First thing. That's the first statement here. Second thing is, if the spectrum is completely included in the half plane, the complex half plane with negative real part, then what we're going to have is convergence of anything which is close to, actually even not that close, but I mean convergence towards 0 of any solution. Now, if for some reason one of the eigenvalue is positive, or has a real part which is positive, then u of t may diverge for some initial condition. Okay? So that's what we have. And remember, in English, 0 is not positive and is not negative. This is a faux ami. No? It's a false friend. I mean, positive is not translation of positive. Translation is non-negative. Okay, so if we have a negative, if the real part of all of the eigenvalues is negative, then again, we have convergence. It will be called stable equilibrium. And if one of the eigenvalue has a real part which is positive, then we will have a divergence. It will be called an unstable equilibrium. Okay, so this is what we have. Now, this is what we have for linear ODEs. Now, in general, ODEs are just what they are. And as I said earlier, for the pendulum, we don't have a linear ODE, right? I mean, unless we have a very small variation in the angle. So let's actually look at what we have for nonlinear ODEs and just look at the theoretical solution. And I will start with some definitions. Okay. So let's actually set the framework here. We'll start with T0, which will be given. That's where we start the experiment. T equals T0. We could simplify and say T0 equals 0, but let's be general here and say T0. I will put the 0 as an exponent, not because it's an exponent, but just because we want to keep the subscript for later. As a matter of fact, I can explain to you why we're doing this now. When we'll do PDEs, often what we have is space variables and time variable. And the space variables will use the index for the space variable, and we will use the superscript for the time discretization. So for this reason, we just keep to be consistent with further classes and PDEs. We're going to put all of the indices, if you want, as a superscript. So I hope it doesn't bother you. So we're going to choose an interval, an open interval, and now you know what open means because you had a class on topology just before this one. Then you have an open interval containing T0. U will be an open set of RD. So D equals to 1, then it's obviously in R, and if D is greater than 1, which is often the case, then you're just in RD. And then you take a function f from I times U to RD that you take a y0 in U, and you consider this this IVP, initial value problem. Y prime of t equals f t y of t and you have the initial condition, y of t0 equals y of 0. So let me just give you an example, because it's very simple, but it's like just theoretical, but it's very, very simple. So if you choose y prime of t equals 3y of t plus t squared, and the initial condition y of 0 equal 1, that means you choose t0 equals 0. The interval can be just r. You could restrict it to something smaller, but I equals r works. D equals 1, so that's very simple here. U equals r raised to power 1, basically r. Y0 equals 1, and the function is ftx equals 3x plus t squared. Okay? Is that clear for everybody? Okay. Let me give you another example. Let's go back to the pendulum for 1 second. So the pendulum. The equation is theta second plus g over L sine theta equals 0. At first, when the person was like taking the pendulum, it was like an angle of pi over 2. But we did not start doing this, right? We just let it go. So the velocity at start was 0. And we choose t0 equals 0, I equals r, d equals 2. U of t is theta of t and theta prime of t. As you can see, we just went from a second order equation to a first order equation. And that what we have is f of t x1, x2 equals x2 and negative g over L sine x1. Now, because I'm lazy, I just, rather than just putting it in vertical and just putting it horizontally, and I put a little t to say transpose. Okay? So this is what we have. Now, from there, I would like to introduce what we call the slope field. The slope field is very simple. For any t and for any x, I want to look at the slope of the solution. It's very easy. So often we normalize it, but I mean, that's very easy. What we have is at every point here, I can say, if I put t, so in the x-axis that's t, and the y-axis that's going to be x here. So what I have is for each point that I can choose, I will have the slope of basically the tangent to the solution. Now I know it's a tangent because I know y prime equals f of t u of x, y of x. So that's what we have. So the curve of a function y, which is a solution to the Cauchy problem, so the initial value problem, is going to be called an integral curve of the slope field. You will also find the name orbit. And let me actually show you this. If you look at y prime equals 3y's plus t squared, and I choose y of 0 equals 0. So what I'm doing here is I'm starting here with y of 0 equals 0. And what I'm having here is the trajectory going throughout that point. Right? And what I know is that at every point on that graph, the solution has a tangent. The tangent is represented by the slope field. Right? So that's what happens at y of 0 equals 0. Now, if I wanted to, take a different initial condition, say I take y of 0 equals 2. That's in green. Y of 0 equals 2. What happens? I just start at 0, 2, and that the solution is going through that point. Okay? So, and again, vectors of the slope field are tangent to the orbit.